Our previous imagination of the universe was completely wrong. In 1977, using technology older than a brick phone, humanity launched 2 probes into space. They have been flying for 48 years, and finally helped humanity touch the solar system's edge. But the images and sounds transmitted back left the NASA control center in dead silence. This top interstellar mission took humanity 50 years and cost tens of billions. Has the great secrets of the universe hidden in every detail. Our protagonists today are those 2 space-living fossils launched in 1977. Voyager 1 and Voyager 2. Right now, they are drifting at the furthest edge that human creations can reach. In a bizarre space that even top NASA scientists describe as incomprehensible and unpredictable. Sending back strings of data that completely shatter our worldview. Some new followers might not know these 2 grandpas. So let us give you a quick briefing. In August and September of 1977, NASA launched Voyager 2 and Voyager 1 in succession. Why did Voyager 2 fly first? Because scientists had calculated a once-in-a-century planetary alignment window, which allowed them to use the gravitational slingshots of Jupiter, Saturn, Uranus, and Neptune to accelerate and complete the exploration mission of the 4 planets. The goals set for them were incredibly simple: fly by the 4 major planets, take some pictures, and measure some data. The mission cycle was only about 5 years, and no one dared to imagine that these 2 probes, carrying obsolete instruments from the 1970s, could actually achieve ultra-long standby up until 2025, and even flew out of the solar system's shield to break into interstellar space. Here comes the key point. As of November 2025, the positions of these 2 old buddies are beyond imagination. Voyager 1 is speeding through the universe at 17 kilometers per second. What concept is this speed? It can run around our standard 400-meter track more than 4 times per second. And traveling from Beijing to Shanghai would only take a bit over 1 minute. Right now, it is a whopping 169 astronomical units away from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. Converting this into an understandable distance, it is equivalent to making 84 round trips from Earth to the Sun. It takes over 19 hours just for light to travel from it back to Earth. Although Voyager 2 is slightly slower, it is no slouch either, traveling at 15.3 kilometers per second. It is 139 astronomical units away from the Sun, and its light signals take 16 hours to return to Earth. Most crucially, both probes have crossed the heliopause that humanity has dreamed of reaching. Simply put, it is where the solar wind can no longer blow, which means breaking out of the magnetic bubble that the Sun uses to cover the system, and officially stepping into interstellar space, which only existed in theory. But the bizarre thing is that their experiences crossing this barrier were actually completely different. This immediately left astronomers worldwide completely baffled. My friends, let us first talk about Voyager 1's cliff crossing. On August 25, 2012, NASA scientists suddenly discovered that the particle data sent back by Voyager 1 instantly reversed. In the months leading up to the crossing, the solar wind speed around the probe had been slowing down, gradually dropping from over 300 kilometers per second to nearly a standstill, and the magnetic field became more orderly, just like entering a buffer preparation zone. As a result, in just an instant, the data suddenly changed its face. The number of high-energy cosmic rays from the Milky Way directly soared by 5%, while the number of low-energy charged particles from the Sun plummeted by more than 90%, almost disappearing. At that time, the NASA scientist team was ecstatic, yet they disbelieved it. So they verified it for months before confirming Voyager 1 had truly crossed the heliopause. This way of crossing was not at all the gradual transition predicted by previous models. Instead, it was like reading a book in a quiet library 1 second, and the next, being thrown directly into a noisy train station during Spring Festival. There was no buffer, and all data instantly shifted gears. This means that in the direction Voyager 1 crossed, the heliopause was not a gentle slope at all, but an extremely steep space cliff. Stepping across it meant a completely different cosmic environment. And 6 years later, which was November 5th, 2018, when Voyager 2 crossed the heliopause, what it experienced was a gentle slope transition, an entirely different style. It took a full few weeks to complete the transformation from inside the heliosphere to interstellar space. The cosmic rays from the Milky Way increased slowly, taking nearly a month from the start of the rise to reaching a stable state. The solar low-energy particles also decreased gradually, rather than vanishing instantly. Even the direction of the magnetic field deflected bit by bit, before stabilizing in the magnetic field of interstellar space. It was like walking down a long flight of steps, where you felt subtle changes with every step, rather than jumping off a cliff directly like Voyager 1. The different experiences of these probes directly dealt a fatal blow to all previous heliosphere models. Previously, scientists generally believed that the heliopause should be a regular, spherical bubble wall, just like the soap bubbles we blow, with similar thickness and shape in all directions. But as it turns out, this thing is not regular at all. Instead, it is like plastic wrap that has been crumpled then smoothed out. Steep like a cliff in some places, and gentle like a slope in others. It also changes with solar activity and the pressure of the galactic interstellar medium, constantly stretching, shrinking, twisting, and denting. What drops scientists' stars even more is that interstellar space is not at all what we imagined, as empty and completely dead. In our inherent perception, once leaving the care of the sun, the universe outside should be cold, quiet, and completely calm. But data set back by the Voyager spacecraft tells us dead wrong. Interstellar space is not only not quiet, but lively. Filled everywhere with turbulence, shockwaves, and irregular particle streams. Both Voyager 1 and 2 detected that outside the heliopause, there are large areas of turbulence, like vortices in the universe, where particles move in a chaotic manner. They also detected traces of shockwaves left by solar eruptions decades ago, just like ripples that haven't dissipated since a stone was thrown into the water. Even more bizarre is that the intensity of particle streams changes with no pattern at all, sometimes surging suddenly and sometimes dropping abruptly, completely defying logic. None of the previous theoretical models could explain this phenomenon. There is a more absurd discovery. The plasma temperature outside the heliopause is as high as tens of thousands of degrees. Hearing this, some fans will definitely ask, Lama, thousands of deg? Why didn't the probes melt then? This goes against common sense. Don't worry, we'll explain this knowledge point thoroughly today, ensuring that everyone can understand it. Temperature in space and temperature on Earth are completely different. Temperature on Earth comes from the dense collision of molecules, whereas in space, the particle density is extremely low. In every cubic centimeter of space, there may only be a few to dozens of particles. Even if each particle has high energy, meaning high temperature, because the quantity is too small, they cannot transfer heat at all. To use an analogy, it is just like using a lighter to light the air. The lighter's flame can reach hundreds of degrees Celsius. But because air molecules are too small, they cannot transfer heat to you. But the heliopause is not as thin as people as previously predicted. The high temperature detected by Voyager follows the same astonishing thickness and complex structure. The energy of individual plasma particles is very high. The heliopause was like the skin of a soap. But the particle density is too low, with a thickness of perhaps only thousands of kilometers. But the data set back by the probe shows. So where does this high heat come from? This layer is hundreds of thousands of kilometers. It is collided out by the solar wind and by the interstellar medium. Some layers allow a small wind to run outward at hundreds of kilometers per second, while other layers block interstellar particles. While the interstellar medium also has its own pressure. In some places, the magnetic field is intertwined and twists magnetic bubble. while in others it is relatively stable. The heliopause. In some regions, the sun's violent decays rapidly, compression occur, while in other regions, a rebound occurs. Particles are continuously compressed and energy still briefly affects. So the temperature soars to tens of thousands of degrees. Is like a multi-layered nested space set, which like when we pump up a bicycle tire, where the environment of each layer the pump becomes hot, complex beyond all scientists' expectations. The air is compressed, internal because Voyager 1 and Voyager 2 crossed at different positions. Except that they passed different. The scale of this process is unimaginably vast. This discovery directly forced decades of heliospheric physics theories to be completely rewritten. What is most admirable is not even these cognition-shattering discoveries, but these two antique probes themselves. Launched in 1977, they have worked for a full 48 years by 2025, making them older than most of our parents. All the instruments on them use 1970s technology, which, looking at it now, is more outdated than the old radios in our homes. Yet they are surprisingly still holding on, still sending value.